All right, so today we're just going to quickly finish up the demonstration that we were working on last time that you basically duplicated with a different recurrence relation in your lab yesterday. Remember that we were using memoization in order to eliminate the redundant recursive calls to make it more efficient. So that instead of taking, centuries or years or whatever, it would actually execute, in a matter of moments or a matter of seconds. So the idea here was that we're going to call Fibonacci with memoization on n, but we're also going to be passing in a table of values so that once you compute that value, you store that in the table so you don't have to recompute the value again. Remember the way that it worked, that we are going to use that cache as a table to compute to store Fibonacci values, right? Cache of 1 will be the Fibonacci of 1, which will that's one of our base cases, 1. Likewise, 2 is going to be Fibonacci of 2, which is 1. And in general, Fibonacci of n is what we're interested in here. That's what we want to compute. So if it's not if it's not 0, then that means that we've already computed it. That will be our flag value to indicate that it has already been computed, or that it's not been computed. And in which case we go ahead and return that. Why? Because 0 never appears in the Fibonacci sequence. So we've not already computed it, so what we do is we pay for the recursion. We say, all right, fine, we'll go ahead and compute Fibonacci of n minus 1, compute Fibonacci of n minus 2, but remember that we need to pass in that cache as we're going along here, okay? Then once we've got those answers, we can go ahead and add those together, put that into the cache before we return, right? So that that next time we ask for it, it'll now be computed. What we need to do in the main here now is actually compute that, or to set up that cache so that we can use it in our recursive calls. So how big of a table do I want if I want n element? Remember, 1 up through 80 here in this case. What am I doing with cache of 0? Cache of 0, right? Ignored, right? Because the Fibonacci sequence starts at 1, 2, 3, 4. It's a mathematical sequence, and mathematicians like to start their indexing at 1. We're not mathematicians. We are computer scientists. So what do? We start our indexing at 0. To accommodate that, I'm simply going to ignore that. So if I want from 0 up to n, how big of an array do I actually need? 5, right? 0, 1, 2, 3, 4. Is that going to give me 5? Nope. What do I want? Plus 1. Don't confuse that with strings and accommodating the null terminating character, right? I'm just doing this so that I don't have to use zero indexing. So let's go ahead and create a long star cache. A call to malloc here. Size of long, right? Times how many do you want? N plus 1. Right. Now, is this correct? N plus 1. That's one of those bad maths. Why? The multiplication only applies to n, not to 1. So what will this end up doing? That'll end up allocating enough space plus 1 more byte, which is not what we want. We want a full additional number there. Okay? All right, once I've got that, I can go ahead and pass it in. But before I do, cache, what else do I need to do? What's stored in that array right now? A bunch of zeros? Maybe. 9 times out of 10, 99 times out of 100 maybe. But uninitialized memory. If I just create a variable, what value is in x right now? Who knows? Garbage, 0, could be, right? Could be anything. So let's go through and make sure that we have, if we have an assumption on what's in that table, we need to make sure that that assumption is correct. I'm going to go ahead and go for each element, for int I equals 0, I is less than n plus 1. Remember, it's of size n plus 1, I plus plus. I will set my cache of I to be that 0 value. I've not yet computed it. Right? You can use 0, you could use -1. A lot of people were doing that in their lab. You could use anything basically that indicates that this has not yet been computed. All you do have to do is be consistent about it. 0 or -1. I also need to take care of my base cases, right? So cache sub 1 will end up being 1, the first Fibonacci number. Cache sub 2 will end up being 1, the second Fibonacci number. All right? GC demo all of this. There we go. And now I'm going to be computing the 80th Fibonacci number. Let's go ahead and look that up and see what it is. Fibonacci of 80. Right. We don't need to look at it all, but it starts with a 234 and ends with a 685. So let's go ahead and execute that. 234, 685. Looks like it's good to me. Right. Of course, we can still hit a limit. 100, right? That's going to end up being some negative value here. Even though it should start with a 354 and end with a 075. Right? Why? Because you still have limits. Right? You still, it's not a negative value, but it's definitely not the correct value. Right? You still have limits. You can't, this is a 64-bit number. Meaning that you can only represent, what was it, 9 quintillion or something like that? That's definitely larger than 9 quintillion. 354 quintillion, in fact. Right? So you're always going to be hitting this roadblock of, okay, well, just make a bigger integer. Just make a bigger integer, right? You're going to hit a roadblock at some point. So what do you do in practice? If you actually need huge numbers like this. Did anybody do the advanced activity? Or try it? Or read it? No? Okay. The advanced activity was to bring in a library called GMP, which is the GNU Multi-Precision Library. Basically, if it defines different numbers so that it detects if an overflow is about to happen. And if it does, it allocates more memory for a larger number. Right? Now, that comes at a cost. It's all done in software instead of hardware. Hardware, 32-bit numbers, 64-bit numbers, those are extremely fast. All the operations on those kind of numbers are super fast. But when you do all of those operations in memory in software, it gets really, really slow, or it can be slow, right? Noticeably slow. But that's how you can do it. You have to bring in a library, a multi-precision library to handle that. Right? All right. Questions on recursion? No? Then let's start talking about the last topic for this course, the last main topic for this course. We might actually get to other topics at the end, miscellaneous stuff like graphical user interfaces, database connectivity, and or parallelism, multi-threaded programming. But in any case, this is the last one that we're going to have actual graded material on. Okay, and it's going to take up maybe 2 weeks, so we'll definitely be doing this after the break as well. And it's searching and sorting. We're going to focus on these two basic operations because they are two fundamental operations when you are operating on data. Just like, subtraction, multiplication, division, addition, all of those are fundamental operations to math. When you're talking about processing data, the two fundamental operations are searching for something, and then, of course, with a collection of stuff, you are sorting that stuff. And processing data is fundamental to computer science. So fundamental that we now have an offshoot called data science, right? Just to focus on the processing of data itself rather than the computation, right? I do believe that we have a data science major coming online next year, right? So if you're interested, check that out. Although you've started out in computer science, so I'd suggest staying with that. But anyway, it forms the basis or a pre-processing step for numerous algorithms. There are lots of other algorithms that process data, and then they'll assume that you can find something, or they'll assume that you can that the input is sorted in a manner that makes it advantageous to the algorithm and improves its performance. Right? And another reason that we look at searching and sorting is that a huge variety of algorithms have been developed. All you have to do is search for sorting algorithms on, say, YouTube or some other popular sites, and 50 different videos will come up with 50 different algorithms and different visualizations and stuff like that. If you go to sorting algorithm visualization, or if you just Google for that, you'll see about a dozen algorithms. All of them are visualized in some manner. On YouTube, there are even dancers demonstrating how each sorting algorithm works and stuff. It's a novelty. And that's why we like looking at it, because there's a lot of different strategies. Divide and conquer strategies, brute force strategies, decrease and conquer strategies. There are at least a half a dozen sorting algorithms out there. Right? We're only going to look at a small subset. Before we get there, though, we need to understand what an algorithm is. Right? An algorithm is a finite sequence of operations that defines a computational process for solving a problem. That's a dictionary definition. Right? That's not a mathematical definition. It's not a computer science definition. It's what you would pull out of Webster's. But for us, it's going to be okay for our purposes. All algorithms must be correct, right? And finite. Infinite loops don't count. That's not an algorithm. That's not a valid algorithm, at least, right? Algorithms are not the same thing as problems. Problems are the sorting problem. Given a bunch of stuff, you want to arrange it in some sort of an order. That's the problem itself. There are dozens of solutions to that problem, okay? And so an algorithm is not a problem. An algorithm is a solution to a problem, right? There may be more than one correct algorithm, in which case you have to look at which one is better, right? And that's where efficiency or complexity comes in. We will be looking at all of those issues as we proceed here. The first thing I want to do, though, is look at a basic searching operation. Okay. So let's just do this in the context of C over here. If you want, yeah, I'm going to go ahead and get rid of all this now that we're done with it. There we go. All right. And get rid of that too. There we go. All right. So what is the basic collection in C? A collection of stuff. We call that what? An array, right? So 6, 4, 9, 3, 2, 3, and this one is in particular is an integer array. 1, 2, 3, 4, 5, 6, 7, 8. I just want 8 elements there. Okay. Keep it simple. So, what does it mean to search this array? What might you be interested in? Think back to Hack 7. You did it already. Right? Given a key element, int key, let's say 3. No, let's go with 5. There we go. Right. Given a key element, search through the array and tell me whether or not that key element exists in the array. Hopefully you remember doing it. Right? What was that function that you wrote called? Contains. Right? Here's an array. Here's its size. Here's a key. Does this array contain that key? Right? You've done this in other contexts as well. Right? Here's a string. Does it contain a capital X? Does it contain a particular character? Right? So in other words, searching is a lot more than just looking at an array. You could look at a string, right? So when you're talking about searching, you have to ask yourself a bunch of questions first. Let me pull something up here first for myself. There we go. Bring it over here. All right, searching. So as far as preliminaries go, right? So what does searching mean? Right? What are you searching for? What are you searching? Right? Are you searching an array? Right? Well, that's what we're searching for in C. But there are plenty of other programming languages, including C, that have other data structures. Right? For example, a list, a set, a map, etc. Right? Now, those are not directly supported in C, and we haven't looked at any of those kind of data structures, but they do exist, and they're not arrays. For example, a list is a dynamic collection that is ordered and then can grow or shrink automatically as you put stuff in or take stuff out. A set is a collection of unique elements. So for example, over here in our array, we have 1, 9, 2 9s. We have 1, 3, 2 3s. Right? A set would not allow that. A set would say that everything has to be unique. And so an attempt to put in a 3 when a 3 already exists in there would be a no operation. That's what a set is in math. And it's what it is in computer science. A map is an even more general thing. If you've ever had any Python experience, they call them dictionaries. They're actually neutered maps. A map is where you can map a key to any value, right? You can map anything to anything. Right? Those are super useful data structures, and they're something that we'll definitely look into in, say, computer science 2. Unfortunately, over here in C, we really only have an array. Right? What are the elements you are searching for? Right? Or searching among, I should say. Right? Integers? Right? Doubles? Characters, right? You're searching a string. Airports? Teams? Right? So what are you searching? And finally, how are you searching? Right? For example, what if it were students? How could you search for a student? How would you typically search for a student? I'm trying to find a particular student in this class. What would I do? A name? All right. That's always been a problem on Piazza because some people just use their first name, and guess what? Well, nobody ever called me Chris in school. Why? Because there were 10 other Chris's, right? We all went by last names, right? It's just there are 50 different Johns, not in this class, but you know there are common first names. Would I be successful searching for John Smith? Probably not. Right? But you could do it, right? Name. What's another way? How do you an NUID? That's how you uniquely identify a student. Maybe a social security number if you have it, right? Maybe a GPA because you're not looking for a particular student. You're looking for a student with the highest GPA or something, right? Are you searching for a particular element? Element, sorry. X, right? Are you searching for the largest or the maximum, or minimum, or median element? Right? That's a search problem too, right? I want to find not a particular element, but I want to find the largest element, right? The person whose last name comes last or something, right? You could all find all instances, or the first or the last instance, etc. Again, in that example that we've got here, we've got 2 9s. Which one of them do you want? Either or, I don't care. The first one, let's say. No, I know. Now I want the last one. No, now you know what? I want all of them. I want to know where all the 9s exist in this array. Right? That's another problem, but it's the same basic problem, right? All of these things are the same basic problem. It's the same basic search problem. It's just that the criteria changes each time. So let's come over here and choose a criteria, okay? How are we going to search through to find that key? So you've kind of already done, what was the version that you did before? Contains, right? What did you take as input for contains? The array, const, int star, array. What else? Size, int size, and what else? The key, the thing that you're searching for, right? And the behavior of this was, and I'm not putting in a return type yet because we are going to change this, right? This searches the given array of size, of the given size for the given key element. Right? It returns. Well, with contains, what did it return? Simply just true or false. True if array contains the key. Right? True being what in C? Well, false is what in C? 0. What's true? Anything else, right? In particular, 1. Or you can bring in the standard Boolean library and use the keyword true. Okay? What's an alternative? That's the one that you did. We won't do that one. Oh, okay. It returns the index at which it finds the key, if it exists. If it doesn't exist, what could I return to say, nope, doesn't exist? Before you returned false, right? For the contains version. What about this version where we're looking for the index of that key? Negative 1 would be a good choice. Why? Because that's not a valid index. Right? All right? Negative 1 if no such element. I like those. Is there a third way that we could do this? The C style way, where C says, yeah, I found it. It's over there. What am I doing? I'm pointing. Returns a pointer to the element. Right? If it exists. If it doesn't exist, what could I return in that case? Null, if no such key element. Right. Let's go with the second one here. Okay? In which case I will be returning an integer. Right? And I want the index of it. Okay? Suggestions on how to go about doing this. If you remember your code, it should be pretty straightforward here. If you want to iterate over an elements in the array and look for a particular element, what do? An idiomatic for loop. For int I equals 0, I is less than size, I plus plus. Right? If the thing stored at index I is equal to the key that you're searching for, then return the index at which you found it, I. Otherwise, if you get through everything and you don't find what you're looking for, return negative 1 as we just identified. Okay? Let's see if it works. Index of. There we go. Int index, right, is equal to index of the array of size n, searching for the key here, and then let's print that out. Printf found element %d at index %d, and the line. So element will be our key that we're searching for, and the index at which we found it will be index. There we go. All right. Now we're going to find 5 where? At 7? Right? There we go. Because it's the last one. It's the last place you look for it. Huh? What if I change this to, say, 9? The way that I've written it right now, I'm searching for the first occurrence, because the first time I see something that matches that key, I immediately return. So what's it going to output here? Predict. 3? Or no, 2, right? If I'm searching for 9, there we go. Yep, 2. All right. What if I search for 42? An unsuccessful search. What will this end up returning? Negative 1. In which case we need to rewrite the message. We did not find it because the index was negative 1. I'm going to leave it like this because simple enough. Right? Oh, now the problem has changed. Right? It's one of these variations now. One of these 50 different variations, combinations that we identified. I'm no longer searching for integers. Now I'm searching for doubles. Right? So let's create another array here of exactly the same size, BRR instead. 6.4, 4.3, 9.8, 2.2, 3.6, 9.0, 3.2, 5.8. Right? And now maybe my key element is no longer an integer. Now it's, I don't know, I'm going to search for 9.0. There we go. Is this going to work still? Is it going to compile? Probably not. At least there's a warning, right? What would I need to do to change this? I don't want to lose the original code here, so let's copy pasta. Seems like a bad, icky idea already. Right? Can I use the same name? No. This will be index of for doubles, right? For doubles. And it'll take not an integer array, but a double array and a double key. There we go. Do I change a single other line of code? No. It's all the same. Right? For int I equals 0, you iterate over the array. You use the same equals here. If you find what you're looking for, you return. Otherwise, you return negative 1. Right? Probably should rename this to index of for integers. Great. Now let's do it again for characters. Now let's do it again for students. Now let's do it again for airports. Now let's do it again. Now let's do it again. Now let's do it again. Am I going to be cutting and pasting this crap all over again? No, I don't want to do that, right? The only thing that would change for those other things would be the criteria by which I am checking my key element. Right? Is this the student you're looking for? Well, I've got an NUID of 123. I've got an NUID of 123. Yes, they match. I've got an NUID of 123. I've got an NUID of 567. They don't match, right? The only thing that I would be changing here is this criteria for checking for keys. It seems like I don't want to be going down that path, right? So let's rethink this and think more abstractly, all right? What I'm going to do, there we go. All right. What I'm going to do is write some fake code, some pseudocode, right? I'm not going to write in any particular language here, okay? Because if I were to write in a language, then I would actually be coding, right? And I would be stuck in that language without that language's particulars, right? You're talking about specifically one implementation for one type of thing, an array or a list. You're talking about one implementation for integers, one implementation for doubles, et cetera, et cetera. I want one implementation, generic and free of any particular programming language. For that, I'm going to develop some pseudocode. Right? So what does pseudo mean? Fake. Latin? I don't know. Latin, Greek, whichever one it is, whatever. And then code, of course, is code. It's fake code, okay? I'm not going to write real code here. Good pseudocode will clearly label the input and clearly label the output. I can give myself some more room here. It's not going to be big. Input and output. Right? My input here, is it going to be an array? No, I want to keep it generic. Right? I'm going to call it a collection. Right? Well, what is a collection? A collection can be an array. A collection can be a set. It can be a map. It can be anything. A collection A equals A1, A2, A3, dot, 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 AN. Okay? So I kept it general. Did I say what those were, by the way? Are they integers? Are they doubles? Are they students? Yes. Right? It can be whatever you want. Right? A collection and a key. Okay. Right? And my output is going to be an element A in A such that A is equal to K. Did I use equals equals? No, because they're not necessarily numbers. Right? It could be a student and a student. Whatever equals means, I'm keeping it generic, I'm keeping it abstract. Right? In the event of an unsuccessful search, I'm not going to return -1, I'm not going to return false, I'm not going to return null. Right? Those are language-specific constructs. Instead, I'm going to return a mathematical symbol. Does anybody know their Greek? That's phi, right? Phi, if no such element. Right? So, Greeks and mathematicians are well versed in their Greek alphabet. Right? You should be too. Right? All right, so there's my input, there's my output. For each A in A. Right? I'm not going to bound myself by a traditional idiomatic for loop in C. For int I equals 0, I is less than whatever. Right? That's actual code. This is pseudocode. I can use plain old English along with mathematics, mathematical symbols to write a more generic, more abstract idea of how to go about doing this. And that's how I describe an actual algorithm. Right? For each A in A, if A is equal to my key, then I will output A. Note here I'm not returning from a function because this is not a function. It's an algorithm. Right? I stop and output something. Okay? Am I using, it would be very, very Pythonic if I did that, right? Colons everywhere. This is not Python. If it were C, what would I be doing? Opening, closing curly brackets. This is not C. So what am I going to do? Something completely different. Something that you can't even type up. Vertical lines with a little indentation over here to indicate that that's where the code block ends. And I'm using indentation. Over here, I don't believe you can do it in the VS Code version, but in a lot of modern IDEs, you can actually collapse the definition of a function, and it'll actually have this this vertical line with the indentation down there to indicate something like this. Right? The reason that now there are no rules for pseudocode. Right? If there were rules for pseudocode, guess what? You'd have a programming language, right? And so because there are no rules, what I'm doing is I'm adopting a style from LaTeX, which does have rules for typesetting algorithms like this. Right? But I choose to use these because there's no way that there's any programming language where you would be able to type this out. It is absolutely abundantly clear that this is fake code, that this is pseudocode. Right? Now at the end, if I don't find what I'm looking for, I output what? That fee. There we go. There's my algorithm. Take that and translate it to C, like we just did. Take that and translate it over to Python. Take that and translate it back to C, but instead of integers, do it for doubles, do it for students, do it for whatever, right? That is as generic as it gets. That's an algorithm. Okay? That's pseudocode. Now, because we are generic and we're, outside of any programming language, we can start talking about that other part that I was talking about before. Once we've got an algorithm, is it good? Is it efficient? Right? How efficient is it? Okay. So the first thing we need to do to analyze this analysis is to capture the notion of work. Right? So what work is the algorithm doing? So what are we doing over here? If it helps, you can look at a more concrete example here. In C, what work are we doing? So we come into this function, we've got a for loop. We've got an assignment operator, okay. We've got a comparison here to see should we continue going in this loop or not. We've got an increment operation, meaning that we're doing an addition by 1. We've got another comparison here, in which case we return. Down here, we just have a return statement. Each one of those things, if you were to look at, say, the assembly code that actually runs in a processor, each one of those operations takes some time. That's our resource. It's doing some work on the processor. It's taking 5 nanoseconds or whatever for each one, right? Which one's the most important, though? I don't want to focus on 1, 2, 3, 4, 5, 6, 7 things. I want to focus on one thing, the most important thing. Generally, we don't look at the things that are necessary for the control structure of the algorithm. This index variable here, yeah, we're doing comparisons on it. We're doing additions on it. We're doing one initialization. But, that's all necessary to actually implement a loop. We're doing something inside that loop that's way more important. What are we doing inside that loop? A comparison. The processor is loading up a variable into one register, loading up another value in another register, and looking and comparing at those values, and then deciding to jump to another memory location depending on whether or not they're equal. Right? Over here, our basic operation is on line 2. Right? So what work is being done? A comparison on line 2. Right? And there's line 2 right there. This comparison. Is this the thing we've found? Right? Or is this the thing that we're looking for? By the way, some nomenclature here. This is our haystack, and this is our needle. Why? Oh, not familiar with that old adage, right? You're difficult finding a needle in a haystack, right? Well, what do? You get a magnet, right? And then you've solved that Gordian knot or whatever, right? All right, so a comparison on line 2. So the question is, how efficient is this algorithm? I'm going to rephrase that. How many comparisons are made to search for the key? Oops. The key. Well, let's come over to the C implementation and look at a particular example. Remember that we start at the beginning. Say that I'm searching for 3. How many comparisons do I end up making? That's not it. That's not it. That's not it. That's not it. There, I found it. How many comparisons did I end up making there? 5? Search for 5. Or let's search for 6. Oh, hey, it's in the first place I looked. Got lucky. So how many comparisons did I make there? 1. Let's search for 5. Not it. 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 There it is. How many comparisons did I make there? 8. Right? 8? There are 8 things in there, right? Okay. All right. Search for 42. Not it, not it, not it, not it. 8 times to get to the end of the array and see that it doesn't exist. Right. Let's generalize that. What about a best case scenario? Best case scenario. Which one of those was the best case scenario that I just identified? When you find it in the first place that you look, and so what are the number of comparisons? 1. I'm going to shorten that to comps for comparisons. 1. All right. Well, what's the opposite of the best case scenario? Worst case scenario. And if it has n elements, right? Suppose the collection has n elements. I want to keep it general. In fact, it does have n elements. Why? Because I labeled it as such. Also, another note here, did I begin my indexing at 0 like a respectable computer scientist? No. What did I do? I started it at 1 like a mathematician. Right? Because this is pseudocode. It's not real code. Okay? By the way, there's some bad language. That's a value judgment there. But there are some languages that do use 1 indexing as their default. MATLAB comes to mind. Any others? What? Say what? Lua. Oh, okay, Lua. Right. For all your Roblox programming needs. Right. Is there anything else that it's used in? I think Steam or Valve used Lua very early, and then I don't think that they use it anymore. Maybe they still do. I don't know. Okay, so yeah, that's all C++, right? Just like Unity used JavaScript and then realized nobody wants to use JavaScript to develop games. And so they got rid of that support too. They got rid of that support, I believe. And it's just C# now, right? Anyway, languages are birthed and they die and they linger, right? But other languages stay the same, right? C, Java, C#, JavaScript, those will be good for another at least 40 years. Right? So the worst case scenario here, how many comparisons will you end up making? N. Either you find it in the last place that you look at the end of the array, or you get unlucky and it was an unsuccessful search. We can't always assume the best case scenario, right? We're not always going to get lucky there. On the other hand, we're not always going to have the worst case scenario. Right? So what's something in between maybe? Oh, okay. What would you call that though? Midpoint or average case? Right? So one naive way of looking at it would be n plus 1 all over 2, which I'm going to simplify here to n over 2. Right? Now that's the expected, right? Now to actually do this kind of analysis for real, you would have to define a probability distribution on the successful search for each index, multiply that by the expected number of comparisons, sum that all up, and once you've done all that complex, it's not that complex of math, but it's definitely not trivial. But once you've done that, guess what? You arrive at the exact same answer as the naive way of looking at it. Okay. Let's graph these. My x variable here will be n. This will be the size of the collection. Right. I'm going to graph this with respect to the work performed. Right. For all intents and purposes, this can be time. Okay? Because if you're performing a comparison, that comparison takes some amount of time on a particular piece of hardware. It takes, say, 5 nanoseconds. So if you're doing 50 comparisons, that's going to be 250 nanoseconds or something like that. Okay? Now, let me go ahead and graph. Well, I'm not going to bother graphing this one. Why? What would it look like? Just a straight line, right? And it's not that interesting. Let me graph the worst case scenario. Come on, snap to 40. There, snap to 45 degrees. Right? There's n. Right? This is the worst case behavior. Right? What is the average case behavior going to look like? We can graph stuff, right? Right there, maybe. Somewhere in there. And that's n over 2. This is the average case. Now, what's the interpretation here? If you've got a certain amount of elements in your collection, it's going to take roughly half the time in the average case versus the worst case behavior. All right? But does it really matter at the end of the day? Tell me about these functions. What kind of functions are these? Hint. What kind of function is this? Come on. Snap. All right. Don't snap. All right. Concave up, but can I move that down? There we go. Concave up, but it looks like this. Something like this. N squared. What kind of function is that? Quadratic, right? It's a quadratic equation, right? Because its power is 2 here. So, with that nomenclature, tell me what these functions are. These are linear functions, right? Both are linear functions. Right? The only difference is the coefficient out front. The coefficient here is 1. The coefficient here is 1/2. Right? Now we have a name for this thing. Linear search. Right? How good is it? Right? Well, you've got a graph that tells you how good it is. For 1 split second, whether or not you're taking calc, if you're taking calc, great, put on your calc hat. If you're not taking calc or you haven't taken it in a while, don't worry, leave your calc hat off, right? In calculus, right? How do we determine the growth rate of a function? Growth rate of functions are the first derivative, right? The second derivative tells you what? Yeah, acceleration, concave up, down, whatever, right? So what's the first derivative of n? The easiest derivative that's like the first derivative that you get, right? Or maybe the derivative of a constant, right? Maybe that's the first one. But this one is just 1. What's the derivative of 1/2 n? Half. Now tell me about these functions. Constants. Right? Both of them. What does that tell you about the growth rate of these two functions? They're the same. It doesn't matter that the coefficient sitting out front is 1/2 or 1. The growth rate is the same. Okay? Now you can take off your CalCat and look at the actual implications of this. Suppose that I have n, and it's 1,000, or what, I don't know, 1 million elements, right? And you're searching for through an array of 1 million elements. Suppose that it takes time, I don't know, 5 seconds. We'll be concrete about this. Right? It's an extraordinarily slow computer. Right? Now suppose that I double the input size. I go to 2n, which is 2 million elements. What's your expectation? It doesn't matter if you look at which one you look at, right? Because the growth rate is the same. The growth rate is linear. How many seconds should it take now? Takes 10 seconds. Right? In other words, doubling the input size means that you double the time. What if I went to 10n instead, which is 10 million elements? How long would that take now? 50 seconds? Right? In other words, increasing the input size by some factor also means that you increase the time that it takes to do the algorithm by that same factor. Right? Can we do better? We're going to look at a way to do better on Friday. And for that, I'm going to give you an old Price is Right game. All right? So you've got this fabulous prize. I don't know what it is. It's a mystery box or something. And I'm telling you that the price is between $1 and $100. Hint, you all programmed this in your first few weeks. Right? So you guess the price, and if you guess the price, you win the prize. If you guess the price and get it wrong, I'm going to give you some more information. Oh, you guessed too low or you guessed too high. So what is your first guess? 50. Why did you go 50? Because I'm going to tell you that it's lower. Right? What does that mean about your guesses? 51 to 100? You don't have to do those anymore because I told you that it's lower. And now it's between 1 and 50 with just one guess. What's your next guess? 25? All right, it's higher. So 25 to 50, or 26 to 49, technically. Right? And that only took one guess. I'm counting up the number of guesses that you're giving. Right? What's your next strategy? 37? Okay. 37 to 50, ... Right? I'll just tell you now that it's 42. Right? That's always the answer. Right? You should have guessed that, right? When I said that it was lower than 50 already. Right? So what's your strategy? You're always going to the middle. Why? Because the input is cut in half every single time. How can you exploit this to do better searches? Right? Rather than blowing it up by, a factor of 10, is there a way that we can exploit that same idea to get much, much more efficient searching? Right? That's what we'll look at on Friday.